If I give you a pile of numbers and ask you to add them up, the order doesn't matter. 1 plus 2 is the same as 2 plus 1. But what happens if that pile of numbers never ends? Infinite series operate differently than finite sums. We cannot rely on basic intuition to solve them. To evaluate them accurately, we must establish rigorous arithmetic rules to maintain logical consistency. Let's look at the baseline rule for addition. As shown in the formal statement of Theorem 3.47, if you have two convergent series, A and B, you can safely add them term by term. You can also scale them linearly by a constant without breaking the logic. For simple addition, infinite series behave exactly according to our finite intuition. The limits of the partial sums combine cleanly, making the proof of this theorem quite simple. But this predictability disappears the moment we introduce multiplication. If you want to multiply two infinite series together, a simple term-by-term multiplication fails. That approach ignores the cross products. Every term in the first series must interact with every term in the second. Think about expanding a standard polynomial. To find the total coefficient for the x squared term, you group the cross terms whose powers add up to 2. We applied this exact logic to infinite series, grouping cross terms whose indices sum to a target number. This produces the Cauchy product, defined in section 3.48. The sequence, C sub n, is formed by summing those grouped cross terms, but this formula has a strict condition. Example 3.49 introduces an alternating series that converges. However, forming the Cauchy product of the series with itself, the product diverges. The absolute value of C sub n is always greater than or equal to 1, failing the necessary condition for convergence. Multiplication is only guaranteed to work under Merton's theorem, where at least one series must converge absolutely. The order of addition is also unstable at infinity. Definition 3.52 establishes the formal concept of a rearrangement, which uses a one-to-one function to alter the sequence of the terms. Take the alternating harmonic series, shown here in equation 22. It converges to a specific, well-defined sum, which the text labels S. Grab a piece of paper and try a quick exercise. Write out the first 6 terms of a new arrangement, where you strictly take 2 positive terms from that original series, followed by 1 negative term. Your sequence matches equation 23. Algebraic manipulation reveals this rearranged series converges to exactly half our original sum. Reordering changed the mathematical value. This behavior is codified in Riemann's rearrangement theorem. Conditionally convergent series can be rearranged to converge to any real number. Picture 2 infinite reservoirs, positive terms reaching positive infinity and negative terms reaching negative infinity. After picking the target, you alternate pulling from each reservoir to cross the line. Since terms shrink towards 0, the oscillations narrow, forcing exact convergence at your target. Let's summarize the operational laws of series. Straightforward addition is universally safe. The Cauchy product requires at least one absolutely convergent series. Rearranging an absolutely convergent series is reliable, while rearranging a conditionally convergent series is mathematically unstable. Conditional convergence allows the infinite nature of a series to bypass standard arithmetic. Absolute convergence is the anchor that forces infinite series to behave with predictable, rigid logic. If you found this breakdown helpful, subscribe to the channel for more step-by-step deep dives into the principles of mathematical analysis.